So, welcome back to the wonderful world of thermodynamics or thermochemistry. And the reason I call this the other part is because earlier we talked about delta H and Hess's law and just heat exchange between a system and its environment. And today, or in this video, and it's probably going to be a couple of videos actually, because I don't think I can get this into all one, but we're going to review delta H a little bit, and then I'm also going to introduce delta S and then delta G in a little bit. So first of all, just to review what delta H is, it is the change in something called enthalpy. And enthalpy is defined as a heat transfer between the system and the surroundings, and it's always defined in terms of the system. So if the system released heat, then it had a negative delta H. If the system absorbed heat, it had a positive delta H. And it works the same way with delta S. And delta S is a change in something called entropy. And entropy is this wonderful little term that means the messiness of a system. The more scientifically accepted term is disorder, but I like messiness. The messier a system gets, the higher its entropy is. And systems in general do tend to move towards a lower enthalpy. The system wants to release heat, and it wants to get messier. So all of this that we're going to talk about is going to lead us to figuring out whether or not a particular process is spontaneous. And so first, we need to talk about what spontaneous means. A spontaneous reaction is one that proceeds all by itself. You don't have to give it a push. You don't have to help it. It just happens. And so if a reaction is going to be spontaneous in one direction, then logic would apply that it has to be non-spontaneous in the other, meaning it's not just going to happen. And big misconception is someone that thinks, a lot of people think that if it's spontaneous, well then it's going to happen real fast. Like when you put sodium into water, that reaction happens all by itself and it happens very quickly. But not all spontaneous processes are fast. Some of them are very slow. The formation of rust is a spontaneous process. It happens all by itself. You don't have to do anything to that iron tool that you left out on the back porch for a little bit too long. It's gonna rust all by itself. So spontaneous just means that it happens, not that it happens quickly necessarily. It could happen fast, but it's not defined by spontaneity. So just a quick review of enthalpy. Delta H, the change in enthalpy, is the heat absorbed by a system. So if the heat was actually lost, well, then that's a negative delta H. So in exothermic reactions where the system releases the heat, then it's a negative delta H. And in an endothermic system where the system actually does absorb the heat, then we do. It is a positive delta H. And the first law of thermodynamics simply states that you can't gain or lose, or you can't create or destroy energy, and so whatever heat is lost or gained by the system has to be gained or lost by the environment. And don't forget this formula right here. The heat of a reaction, the enthalpy of a reaction, is going to be equal to the sum of the delta H's of formations of all the products minus the sum of all the reactants. And remember, these values right here, you look up in a book. If you don't have a chemistry textbook nearby, but you do have a smartphone, you can simply Google standard heats of formation. And that will inevitably take you to, it'll list hundreds of results from listing this. Just pick one. They're all pretty much the same. And then you just simply set up this very simple addition and subtraction problem to find the delta H of a particular reaction. Well, enthalpy mathematically works really similar to, hang on, I think I said that backwards. Entropy. Entropy works very similar mathematically to enthalpy. But just definition-wise, entropy is the measure of randomness, the measure of messiness, the measure of disorder. And because gases are more random than liquids, gases will have a higher entropy value. So if you are going through the phase changes from solid to liquid to gas, then delta S is going to be positive, because as you move from a solid to liquid, the particles start moving around more and are not locked in into position. Yes, I know they vibrate in place, but the particles are locked into a position. Well, as they start moving around freely, that becomes messier. Liquids are messier than solids, so it is an increase in S, and then the same increase in S as you're going from a liquid to a gas, because these particles are even more disordered than the liquid was. And if you're going the reverse, if you're going from a gas to a liquid, then a liquid to a solid, you increase the order, which means you decrease the entropy. And just another little rule that the S value is higher for more complex molecules. So propane with 3 carbons is going to have a higher entropy value than methane with 1 carbon. And the second law of thermodynamics states that any spontaneous change is always associated with a positive delta S. Yeah, that's just the second law of thermodynamics. The third law is the one that nobody ever knows exists. I don't know why, but no, everybody forgets about the third law. Sorry about that. It's my phone going off. And it states just simply that the entropy of a pure solid is at 0 Kelvin is always 0. And this is kind of a definition, it's almost a definition of S as much as it is a definition of 0 Kelvin. Because at 0 Kelvin, absolute 0, there's absolutely no movement. That vibration that we always associate with the particles in a solid, that's gone at 0 Kelvin. And so you can't get any more ordered than you are at 0 Kelvin. And so that's when S is going to be at its absolute lowest point. And so that's why they, kind of said, okay, well, at 0 Kelvin, we're going to say that S is 0. So you're never actually going to have a negative S value, because things will always be messier than S value, or messier than something at 0 Kelvin. And then as the temperature is warmed above 0 Kelvin, S does increase. And at phase changes, S is going to increase a whole bunch. So I'm going to draw for you guys 2 graphs here. One is your general phase change graph. And that is, let's see, we put energy down here and temperature up here. And so we're going to start from a solid and go all the way to a gas. So we start with a solid, and it's going to begin at some point. And as we increase the temperature, here we'll just start it like right here. As we increase the temperature or increase the energy to a solid, its temperature is also going to increase up to some point where the particles in the solid have gained enough energy that they can actually start to, I don't like to say break the bonds, break the intermolecular forces that are holding them in their solid spots. And so when that happens, the energy being applied is no longer increasing the temperature of the substance, it's increasing just the energy. It's being used to break those intermolecular forces. So at this point, we have solid melting into a liquid. Then once all of the solid is gone, now the energy being applied can continue to increase the temperature of the liquid. So here we just have liquid. Until again, we reach another point where the particles have absorbed enough energy to where they can start breaking the final intermolecular forces and truly escaping into the gas phase. And at that point, the energy is now being used to break intermolecular forces. So we have a liquid turning into a gas. And this will continue until the liquid is all gone, at which point the temperature will rise all the way up to plasma, which is way far from this. And so we'll just have gases floating around in there. And so this is a phase change graph relating temperature and energy. But if we were to do a phase change graph relating entropy and energy, it's going to look a little different. We're going to start off in the same solid. You know what? I'm going to actually just change my color and keep it on the same graph. Let's write in yellow. I like yellow. And so entropy is going to be here in the S. In the yellow. And so what happens is as energy is applied to a solid, the entropy goes up just a little bit, not a whole lot. But then once this phase change starts, the entropy goes up a whole whole lot. And then once we hit a liquid again, these 2 points are supposed to line up, I'm sorry. But once we're a liquid again, it levels off. The entropy doesn't increase as much until we have yet another phase change, and then it's going to increase a whole lot until we're just at a gas, and then it levels off again. And so they're kind of like opposite graphs, because whenever you have a phase change occurring, going from solid to liquid, the entropy changes a lot, and the temperature doesn't change hardly at all. But whenever you have just the state by itself, just a solid, just a liquid, just a gas, the entropy is not actually changing very much, but the enthalpy is. And at this point, I'm going to go ahead and call this set of notes quits, and we'll have a part 2.